Hello and welcome to CUDA Weekly. I'm your host, Johan Bontes. Today I want to talk about efficient data deduplication. Let's say you have some data and you want to remove duplicates, or at the very least, you want to know if there are duplicates in your section of data. Now, there are easy ways to do this, but as we will see, those easy ways are not as efficient as they could be. We'll have a look at ways to speed this up depending on the data that we're looking at. Here we see Compiler Explorer with a minimal bit of code to set up our GPU code and to run CUDA device synchronize. CUDA device synchronize waits until the GPU code is done, and the return code from that we actually return here. You can see true 3.1. That means the GPU was busy and our code did not run. Compiler Explorer is a free service. It doesn't have infinite resources to run our code, so sometimes the GPU is busy with running somebody else's code. The trick to overcome this is just to run it again, and then hopefully we will see 0, meaning that all ran successful, and we'll be able to see the output of our code. Let's put some code in to detect duplicates in a range of data. Let's have a look at the program. First, we start our timer here. Before that, we set I to the current thread ID from 0 to 31 because we have 32 threads. Modulus 5, so we'll have about 7 duplicates on average. Then we generate a dupe mask using match any sync. Now the dupe mask is a bit mask with 32 bits in it, one for every thread. And match any sync gives us 1 bit for every thread value that is the same as the current thread. So every thread gets a 1 for itself because, well, the thread is always equal to itself, and every other thread that matches it. We can see that here, if we look at the dupe mask, the thread 0 has a 1 for itself on the 0th entry, and then a 1 in entry number 5, as we would expect, entry number 10, entry number 15, and so on. Then, just for bonus points, we generate the leader. So we take the first batch set with FFS -1, it's off by 1. The GPU reports that this takes 83 clock cycles. This would be wonderful if that were true, but unfortunately it's not true. In order to get the real value, we need to fix this code a little bit. When we do this, we can see the time has now changed. I'll show you the reason. When we look at the assembly code, we here have our clock statement for the start. We here have our clock statement for the end. Here is a match any. As you can see, that actually translates to a single statement. And here is some calculations to calculate the first bit set and do the -1. All of these things are in the same order that we have in our code. When we remove the volatile, the optimizer will decide to rearrange our code so it has a slightly more efficient layout. But unfortunately, this also means that we now no longer have an accurate time. So what happens is, yes, we have a faster time, but not all of the statements that we need are actually included. This FLO is now placed after the end clock, but the FLO is a part of this find first set statement, and that needs to happen before the clock. So this has now, well, escaped our timing. Let's put the volatile back. And let's change something else. Let's say there are no duplicates in our data. What will happen to the time? Well, that's a surprise. The time now has shot up to 409 clock cycles. That's a lot more. It's doing the exact same stuff. So it turns out that Match Any Sync actually does more work if there are fewer duplicates. Maybe there's some early out that it does, once it's done, seeing that all the duplicates are accounted for. And of course, if there are no duplicates, it needs to actually go through all 32 threads, and it needs to do more work. If we code it up so that we actually go through all 32 threads, we can see that we can do this quite a bit more efficiently. Let's have a look. Hang on, let me fix a few things here. We set it up so that there are no duplicates, which is the worst case for Match Any Sync. When we then run this as a loop, we can see that we only take 331 cycles. That's not better than 400 cycles. And let's have a look at the reason why this is so. Here we can see the code. This is the start clock. Then there is a lot of code. I mean, a lot. And we have an end clock somewhere around here. There, an end clock. Now let's have a look at the code in between. As you can see, there's no loop. The loop has been fully unrolled, even though there are 32 iterations. So that's a lot of unrolling. And the compiler has interleaved the code so that all of these are run as independent statements where subsequent instructions fill up the latency caused by earlier ones. So it's interleaved these things as efficiently as it can. And it can because all these 32 comparisons are fully independent of each other. Let me first run you through the code. Here we have a shared array, 32 masks, one for each thread. We then run a loop 32 times. We set the mask for that particular thread with ballot sync. That sets a mask with 32 bits, one for every thread that is running. And every thread contributes one bit within this 32-bit mask. The bit for our thread is generated by A is equal to whatever the value is for the first thread, for the first iteration of the loop, second thread, second iteration of the loop, and so on. So in every iteration of the loop, all the threads compare their value against the specific value of one particular thread, a different thread for every loop iteration. We thus generate 32 masks, exactly the same masks as are generated by Match Any Sync, except of course that we always go through all of the threads which mask AnySync doesn't do. Async walk makes sure that everyone is done writing. Now we can read the mask for the particular thread into each variable tube mask so that every thread gets the correct mask from the shared array that was built up to begin with. We then return the leader as before, and we return the tube mask as a reference parameter. And we print the same data as before, and you can see here in the output that we get the same data as we got from Match AnySync. You can see that data matches up when we change the data to mod 5, and then the mask looks very familiar from what we saw before. Unfortunately, the time is fixed. So this is still 300, whereas the previous one with Match AnySync took about 100 cycles. So if the likelihood is high that there are no duplicates in your data, and you just want to check the occasional stray duplicate, well, then the loop is more efficient. And if you say, well, the likelihood is that there are lots of duplicates, and I want to see where they are, then Match AnySync is more efficient. Perhaps we have time to look at one more example. Let's say you know that your data is sorted. Then we can do it a lot more efficient, because then the only thing we have to do for each thread is to look at the data of the thread just in front of it. If the preceding thread has the same data, well, then we know that our item is duplicate. The code for this is as follows. Some copy paste here. We've been through this code. Here the semantics change somewhat because we are no longer interested in an exact map of where the duplicates are. We already know that the data is sorted, so we will know that if we are duplicate, our duplicate mirror will be in front of us. So there's no need to create a mask. We can simply keep those that are not duplicate. When we check, we can see that it only takes 35 clock cycles. It's significantly faster. And of course it is significantly faster because we're doing significantly less work. Another nice property is that it doesn't matter what the data is, the time will always be the same. Okay, I would like to leave it here. It's been a much longer episode than I was planning for, but it's not a trivial subject, so I guess that's okay. Thank you for watching. I hope you enjoyed the episode. If you did, feel free to like and subscribe, and I'll see you next week.